In this video, we're going back to force, and in this case, we are talking about pressure of water. So suppose we have a face of a dam or some other plate on a wall. Maybe we have a light under the surface of water and a pool. And in general, we have a surface underwater. And we want to find how much force is being exerted on that plate, on that face by the water. So pressure on a surface is computed as the force divided by area, and force is volume times density times gravity over area. In volume, we know to be area times some depth. And density is rho times g. Since we have these two areas, they cancel each other out, leaving us with this rho times g times d for how far below the surface our plate is. This is known as hydrostatic pressure, pressure of water at rest. Hydrostatic pressure is the same in all directions. So hydrostatic pressure on a vertical wall in a pool at depth d is the same as hydrostatic pressure on a horizontal surface at depth d. So that is if I have this wall and have water pressing against it, or if I have a plate here, the pressure at that point with that water is going to be the same. And ultimately, what that's telling us is we can use this equation to help us, even if this is mostly talking about a surface all the way underwater, d meters under the water, can still use it even if that depth is varying. So finding the force on a vertical surface, such as the face of a dam, assuming water completely covers the surface, we have some water, we have some plate that's under the water, and we want to find the force. Well, force equals this pressure that's being applied times the area. And this is a P specifically. So pressure times area. But pressure is the density times G, so gravity, times the depth under the water times area. Same pattern. We want to figure out all these pieces. Density, gravity, going to stay the same. So let's divide up the surface by the depth. From the bottom of our plate to the top of our water is H. And we have some depth that we're looking at here for our little y minus 1, yi minus 1, yi with a distance of delta y. So we're looking at some depth here for that plate. Same pattern as before. The depth we're trying to find, we know the height of the water from the bottom of the plate. We know we're looking at some distance yi. The depth is equal to the height of the water minus yi. Then area, we're looking at just a two-dimensional object, just a face of something, a flat dam wall, a flat tile underneath a pool. I'm looking at a flat object where the area is equal to a length times width. We have a length here, that's our delta y. What we don't know but could figure out is the width of that little rectangle. So the width at that area yi going to be our area, meaning the force on this little blue rectangle is equal to rho g, their constant, depth is h minus yi, area is the width at yi times delta y. Same pattern, add them all up, take the limit. And this gives us an integral from a to b. That integral is going to be where is the plate? Where are we trying to find the pressure, the force of rho g h minus y, some width function in terms of y, delta y, dy. Did that again. Just like with pumping, the big task is going to be figuring out our width function that will go in. So let's take a look at an example. A plate shaped like an isosceles triangle. So two sides are the same, with a height and base of 1. So the height is 1 and the base is 1. Is placed on a vertical wall 1 meter below the surface of the water. So that's also 1. We want to compute the force on the plate. Based on our drawing, we're going to put 0 at the bottom of the plate, and h is the top of the water, not the top of the plate. So top of the water would then be 2 meters above the very bottom of our plate. If our plate itself is 1 meter high, the top of our plate is at 1 meter. Now, using our integral, the force is going to be equal to the integral from a to b. A to b is where is our plate? Our plate is from 0 to 1. Of rho, that could be 1,000 because we're dealing with water. But we're going to leave it as rho to not worry about that 1,000. Just keep it as a constant. G, again, could be 9.8. Going to leave it as G to keep things simple. H, the height of the water, minus y. And then there's going to be some function for the width of our triangle. Finding this W of y, we have similar triangles again. At any point y, I want to know the width of this triangle. We have ultimately 3 angles that are the same because the width and the 1 are parallel to each other. Meaning when we look at the big triangle, we can look at the height, which is 1, over the width, which is 1, is going to be equal to our smaller triangle, which has a height of y, because we're trying to find the width at any given y, and a width of what we're trying to find. So filling those in comparatively, we have the width divided by y. This implies the width equals y. So our width function in terms of y is y. So we have 0 to 1, rho g 2 minus y dy. That back down here. The width in terms of y is y. Evaluating this integral, we'll actually leave that to you to do the work in between. Remember, rho and g are just constants, but this works out to be 2/3 rho g. We are finding force, so our units will be newtons. And that concludes our final physical application.